Systems for wet processing. Your next level of cleanliness. Your next level of product quality. Your next level of flexibility.
Hello, a very good, nice early morning for this virtual conference, having a nice set of people under the title Industry Presentation.
Good morning.
Good morning.
Good morning. Okay, I hear you all. This is very good. This is now the second round of industry presentations. I think the word industry is maybe a little bit misleading. It's also open to institutes or whoever wants to present innovation, ideas, patents, or whatever might be of interest of this conference and is not directly part of the scientific program. And so I'm quite happy that we have here 5 panelists today, and which will show you a nice set of overview about what's going on in PV industry today, but also in equipment manufacturing and measurement software, I think. And so let me announce the title of this presentation is Atotech, Adding Value with Printed Metallization, and Mrs. Kubitza will present us this talk. It's your floor.
Thank you very much. And thank you also for giving me the chance today to introduce Atotech and our ideas of how we want and can support the sustainable growth of the PV industry by adding value with plated metallization. First of all, since plating is still a bit of a niche in the industry, I would like to take some minutes to introduce us as a company. And then later on, I would like to share our latest results on plated metallization as alternative to silver screen printing. These results have been obtained in a cooperation with the Fraunhofer Institute here in Germany. Some quick facts about Atotech and our world of surface finishing. We as Atotech have been founded in 1993, as we are now, but our history dates longer back in the plating industry. We're going back to the late 19th century, where a company called Schering here in Berlin already did some plating and sold some chemistry on that. Today, we as Atotech are present in more than 40 countries worldwide, and we are a group of more than 4,000 experts in that industry. We serve more than 9,000 customers all over the globe. A big point of our work is also R&D. So we hold a portfolio of about 2,300 patents as of today, and more than half of our R&D projects are devoted to a sustainable growth. Our concept is not only delivering chemistry, but we also want to offer the full package of chemistry, equipment, and local service. We have the opportunity to package our work with chemistry and equipment. We have a strong team to support technical growth, and we are also proud on being innovative and also creating our own compound formulation to match our processes with the different requirements and demands of the application. Here is our presence where we are. So we have 3 regional head offices. Our headquarter here is in Berlin. Then we have a headquarter in Japan and a local headquarter also in Rock Hill in the US. We have a network of 16 tech centers This is our approach to offer the best service also local. Our tech centers are used to scale up our processes to almost production size level so that we can make sure that our processes are fine-tuned and working fine before we release them finally then to the market. Our business is built on two core pillars. So one is the electronics section where we serve everything around PCB, so printed circuit boards, semiconductors, surface modification, all in that area. And the second pillar is we call general metal finishing, where we serve various industries with different surface finishes from decorative applications to corrosion protection, wear resistance, so all different fields. Although you might not know our name Atotech, but I'm pretty sure that we have been in contact this morning already several times. When you just now sitting at your laptops, I'm pretty sure that there's a bit of Atotech in it. Or when holding your mobile phone, there's a bit of Atotech in it. When we look at the sanitary industry, the shower heads, the faucets, also everywhere you see is a bit of Atotech. And last but not least, we're also having our share in the energy industry, in the wind energy, and what I will explain a bit more for sure today is also we want to add value to the photovoltaics industry. So now having told you the story about us, I want to switch now to the plated metallization as an alternative to the silver screen print technology. Let me start with a quote that I've read in the latest ITRPV roadmap. Metallization pastes, inks containing silver are the most process-critical and most expensive non-silicon materials used in current silicon cell technologies. Paste consumption therefore needs to be reduced. Well, this is a statement that I have come across the last days for many times. The volatility of the silver price, the availability of the raw material, and has been discussed many times. And the agreement was there needs to be this topic needs to be tackled and taken into consideration. When we look at the early 2000s, 1% of the global available silver volume was consumed in the solar industry. In 2019, it was already 10%. And where the future will go is not clear, or is there different statements? Yesterday, I heard Mr. Verlinden saying that it might be 100% if you're going into the terawatt scale. So this is really a big point that needs to be considered. The second consideration is the paste consumption. When we're looking at the different cell types and the future cell types that might take over the market. So compared to a PERC cell, the silver consumption of a TOPCon cell is 50% higher. And when we're looking at heterojunction, it's even more than 200% more need of silver consumption. So in here, definitely, we also see that there is work to do to work on this issue. So our idea to tackle this is we offer a plated metallization to reduce the silver consumption to a minimum, or we even see the possibility to eliminate if tin could be considered as the capping layer. I have chosen here the example of TOPCon cells, where the average consumption is named in the literature at around 140 to 150 milligrams silver per cell. Comparing to a a plated cell where we can reduce this down to a minimum of 3 milligrams silver per cell. So here we see a really good chance to save these critical resource. This is what a plated finger would look like under a FIB focused ion beam crosscut. So we're looking here at the laser opens a structure followed by a nickel layer that forms the diffusion barrier and offers the seed layer then for building up the copper finger. And then finally, the fine white line that you see is a flash of a silver cap. Being in production already on certain cell types, we were asking ourselves, is it possible also to adapt this plating technology to new cell types? And therefore, we took the chance to do a technical benchmark on comparing classical screen print with plated metallization on TOPCon cells. So we took the same substrates and they went through two different metallization concept routes. So one is the classical screen printing, and the second one was processed with a flash a nickel barrier of 0.5 microns with NeMate, our sulfamate nickel plating. And then the copper finger was built up with cuprasid PV, which is a copper that deposits low stress and ductile copper layers, so that there is no risk of warpage or and comes with a certain ductility. And the final finish was done with a flash of Argalux PV, a silver process, which can be applied either electroless or with current, depending on what's required. Since the time is too short to discuss all details, I just chose a few highlights. Also, Mr. Kluska has discussed it more in details already in the conference section. So we did 2 sets, around 200 cells each, a glimpse on the results. So we could prove that plating has a better cell efficiency. We received the results that, in summary, the resistance, so here we see the serial resistance sum is better than compared to silver screen print. And one of the mechanical tests was a 4-point bend test with a small laminates. You can see here on the top how it was set up. And here we saw that we have equal results on the fracture stress. And having talked about ductility, I would like to share with you this picture, which I think is quite impressive. So here we see the broken cell, where our ductile copper can maintain the electrical connection even if the silicon cell is broken, whereas the more brittle contact of screen printed will lose the electrical connection. Then certainly we also wanted to see how it is on a module level. So then we created, out of these 200 samples, we chose some cells and set up 2 modules, one plating and one screen printed module. The summary here of the results is that even if we have the screen printing, the parameters for the stringing and everything was set for the screen printing, we could achieve comparable results also with our plated module. And with these promising first results that we have seen, we are now looking also forward to get the next results when we are looking at the different etching and mechanical loading tests, which are on the way. And also having this good results, and for us promising results, as in this first shot investigation. So we are pretty sure that also the future technology, the future cell types are good candidates to be to look at the opportunity of having plated metallization. So this is a glimpse at our portfolio. So we have set up a full dedicated PV portfolio, from mild cleaning to our ductile copper processes, a variety of tin processes, all depending on the requirement. Nickel and silver process is also available. And this brings me to the summary. So what we are seeing with plated metallization, we really see a true alternative next to silver screen printing, because we are able to save critical resources. And this is looking at the volatility of the silver price, quite an economic solution. On cell level, we have seen some technical advantages that it can offer. And having also first production experience on certain cell types, we really think that looking into plating is one response to the request of reducing the silver consumption in the plating industry. And with that, I close my presentation. And I would like to invite you also to our showroom to discuss and show even more details than I could do now in the limited time that we have here. Thank you very much.
Thank you so much, Ms. Kubitza. That was very enlightening, and I think a very good example how to use this industry presentation on a level of I would say device fabrication, which also gives us an idea to save silver. Silver is one of the raw materials that's really starts to get a bottleneck. And as you know, and you mentioned it, this conference has this motto, terawatt scale. And I just figured, meanwhile, what is the current consumption of silver per terawatt? Okay, you are just on the right track. So thank you very much for this presentation. And so I would call now Mr. Laurent Clochard. He is with Neen Photovoltaics. I don't know whether it's Neen or Nines, depending whether it's French, English, or Italian.
Nines Photovoltaics.
Okay, it's Nine. Okay. And your title will be the ADE technology, industrial single-site etching for the post-PERC era. Low cost, high throughput, dry chemical etching without greenhouse gases. So that goes in the direction of sustainability in PV manufacturing. Great to have you here. It's your floor.
Thank you, Heinz. And sorry for the long title.
No, that's good.
Okay, thank you very much. And so we are Nine Photovoltaics, and I am Laurent Clochard, as Heinz said, the CTO of the company, and I'm going to be talking about atmospheric pressure dry etching. Short company introduction. We are an equipment manufacturer and process development company founded in 2010. We are based in Dublin, and we focus on atmospheric processing for the PV market mostly. We're financed through private and EU funds. And a quick timeline, in 2010, we had our first proof of concept for this technology. In 2016, Fraunhofer IAC were early adopter and purchased our first tool. In 2017, we set up a pilot line here in our facility headquarters in Dublin. And after that, we secured more funding to develop an industrial tool. We refocused on poly SEH for TOPCon, and we have just that new tool in our facilities now, going through its phases. So what is the ADE process? The ADE process is a silicon etching process, and we're using molecular fluorine gas, F2, for it. It's an inline tool, and we have a continuous flow of wafers. So We are working at atmospheric pressure. There is no vacuum, and it's an open reactor, so the wafers can flow through freely. There is no plasma and no ion, and it's a low temperature chemical etching. So it's not, although we call it dry etching, it is not RRE. It's very different from reactive ion etching. So there's a number of applications we're looking at in terms of silicon etching, but we are mostly focused at the moment on solar cells. What are the main process advantages of the ADE? Well, it's a very high silicon etch rate. Our configuration provides also a single-sided process, so we etch only on one side of the wafer. It's a very selective etch. As I said, it's chemical etching, so you can use silicon oxide or silicon nitride as masks, and it's a low temperature process. And in terms of industrial suitability, we get a very high throughput, obviously, and because it's a dry process, we have a very accurate process control and stability. And it's all packaged in a very small footprint. We can achieve low cost of ownership through on-site gas generation. I'll talk a little bit more about that later. And we don't use any greenhouse gas, so it's altogether it's a very sustainable process. This is our R&D tool version, the AD100, so single lane tool. This is currently what we have set up in our pilot line here in Dublin. So this is an overview of the reactor itself. So as you can see, it's fairly compact. The overall length of the reactor is about 5 wafers length. You can see here in red the conveyor belt where the wafers are held. And for this system, we can use up to 30% concentration of fluorine F2. This is the system we had installed first in Fraunhofer, and now fitted with new loaders, automation for loaders and unloaders. And as I said earlier on, they have been early adopter, and they're still using that very much at the moment. For an R&D setup, like the 2 previous tools I showed you, essentially the layout is gas cabinets feeding the ADE tool, and you can actually use a dry scrubber to scrub the so passive scrubber to scrub the exhaust gas, and you can actually scrub with a wet scrubber as well if you have that already in your facilities. Talking about process results, we have been focusing on TOPCon. So most of the deposition method at the moment for amorphous silicon lead to partial or full wraparound. So the front side essentially needs to be etched. And for this, you need a robust single-side etch process, but you also need, for the front side, but you also need to target the wafer edges. And you need to preserve the imager and achieve a low reverse current. That's really the goal. So with the ADE, we get excellent selectivity, versus BAG, so something like 1000 to 1. The ADE process, the ADE etching works with doped, undoped, or annealed layers, either way. And we get some etch wraparound on the backside, but only less than 500 micrometers from the edges. And the edges, or from the edges, sorry, and the edges are fully etched. So we achieved a very good parallel resistance at a fast etch rate. This is some same images showing before and after. So you can see the BAG layer under the poly-SE is perfectly intact, and the polysilicon is fully removed. So typical etch rate at 30% concentration, which is what we use in our R&D setup, is 3 to 4 micrometers per minute. So it's quite fast already. This is the reverse bias cell behavior. So after ADE, the thermal analysis shows that there is absolutely no spots, and we can reach quite a high parallel resistance. All shunts are therefore removed. And this is a list of all the batches that we have done recently. And the reverse current values are on target and much lower than 1 amps per cell. So this is really, and you can find more details of those results in the poster that's going to be presented by Dr. Bishar Kafler from Fraunhofer. I think it's actually this morning, called High Throughput Dry Etching of polyacid layers for TOPCon solar cell. In terms of our technology roadmap, currently passivated contact are for the rear side only. The next logical step is for the front side. There is also some interest in IBC, and obviously the perovskite cells, the Bothersam architecture has to be compatible with perovskite. So all these aspects we feel really to more integrate etching steps, and we feel AD would be relevant for that, especially with the good etch selectivity that we can get and the fact that it's a single-sided process. This is another process we have been working on, which is a texturing process. We are still very much developing for monocrystalline application, trying to compete with alkaline texture, but it's not quite ready. But this is still something we're working on. In terms of industrial product, this is our high throughput industrial machine. And as you can see, it's still very compact. And this is a modular concept with 3 to 6 lanes. And this is the conveyor we're looking at here, with rather easy access for maintenance. You can pull out the whole thing out of the tool. You can have 2 various configurations. You can actually put them back to back to move to 6 lanes and increase your throughput. So for up to M4 wafers, you can have 6 lanes and 12,000 wafers an hour. And for M62G12, we have 4 lanes and 8,000 wafers an hour. And that's just a quick comparison of footprint in terms of what you would have compared to an inline single-side wet tool. For production, looking at the fluorine supply, there's several options depending on the capacity that you need per year. So it's either gas bundle for low capacity. You can use on-site generation for 1 to 10 gigawatts, and for multi-gigawatt scales, really, an F2 plant is probably the best way to go. So this is not something we supply. This is gas suppliers provide these options, so it's already there. In terms of environmental impact, I mean, obviously the trend is that we're facing a major PV industry expansion, but also a climate crisis and a global transformation into a CO2-based economy. So it's very important. The footprint is very important when selecting a new technology, especially a water footprint, pollution, and global warming gases. The PV industry water footprint is mostly related to a chemical process. So with our technology, we're essentially offering a step toward the reduction of the PV water footprint and offering a dry process. As I said earlier on, we don't have any global warming gases in our chemistry. When you compare that with typical reactive etching process and plasma process that would use very high global warming gases, we use fluorine with 0 global warming potential. so no global warming impact. Okay, that comes to my conclusion. I presented you the industrial atmospheric dry etch silicon etching. I showed you some results from the TOPCon process, validation of our process and our technology. We can achieve low cost of ownership using on-site generation, and we have a very low footprint. And we feel that this technology is relevant for upcoming cell technologies. And we have a sustainable process in line with upcoming carbon policy, and we hope we'll be moving the industry further toward dry processes. Thank you very much.
Thank you so much for enlightening this. I note at this point, as I was moderating a sustainability panel in PV, it's the second industry presentation displaying the advantages of a sustainable production. And this leads me also, gives me a bridge to our next presentation of, I think, single-loss technology. Let me just look at the details here.
Hello.
Hello, and I think it's we have two speakers. It's Dr. Xue Micheng and Mr. Dirk Beisenhardt. And as it is a longer presentation, this is a double slot. The title is Highly Productive Vacuum Deposition Equipment for Heterojunction and TOPCon Solar Cells. And I was just calculating, you would have both time until 9:32. So this is 29 minutes from now. We are pretty much
very long.
Okay.
Very long.
Well, I got the signal that it's a double presentation, and we certainly want to accommodate the switch there. And I think it's a very interesting scene. So just go ahead. It's your floor, Dr. Chen, and we are listening to the deposition equipment.
Yeah, thank you for your kindly introduction. It will be a long presentation, but hopefully I will not make you too boring. So I hope you can see the full screen of my presentation. Can you see it?
Yes.
Okay, good. Then let's start.
But okay, now it's okay.
Okay, good. So my name is Shumi Chen. So today is very being honored to be here, represent the Singular Technology to present our latest results on highly productive vacuum deposition equipment for heterojunction and TOPCon solar cells. So my presentation will be in general 6 parts. So firstly, shortly introduction our company, and the second is a roadmap for crystalline silicons. I think most people here are quite familiar here with this, so I will skip some of them. And the bottleneck and solution for heterojunction and TOPCon mass production. And the next is our main content for PVD for heterojunction, and also PCVD and PVD solution for industrial TOPCon solar cells. In the end, will be a summary. And here, for our company, our company, Singular Technology, is founded in 1995. Actually, but our technology is coming from even earlier, coming from LIBO technology. So LIBO vacuum. So we have very long history on vacuum technologies. So we have 351 employees, and we in the field we have over 8,000 vacuum machine in the field, especially for the sputtering machine. So our headquarters is close to the Frankfurt. It's a small town called mine, and we also have one subsidiary company in close to Munich, which is focusing on the chemical process. So today, it also contribute a lot for the heterojunction process. And here is our main technologies. So divided into 4 parts. First, thin film deposition and wet chemical process. It's the main technologies we provide for crystalline silicon solar cells. And in the latter is a surface engineering and thermal processing, which is more used for semiconductor and some other industry fields. Today we will focusing on the thin film and wet in the thin film deposition tools. And our technology is mainly divided into three business fields. So here, the first is the solar cells. Actually, as you know, we are the one who can supply almost the whole turnkey for CIGS solar cells. And we have already delivered quite many machines, evaporation, thermal annealing, and sputtering machines for CIGS and gadolinium telluride. So we are focusing a lot before on the thin film solar cells. So today we also provide quite many products for crystalline silicon-based solar cells, especially for heterojunction and TOPCon. So here, both Silex and Linux is a chemical machine which we provide, and the PVD and the PECVD is focusing is our main content for today. And for semiconductor and life science, we are also focusing on the high vacuum deposition tools. And here is our common platform for our vacuum deposition. So both our PVD and the PECVD is inline horizontal vacuum deposition tools. For PVD, we have already delivered machine to heterojunction factory. It's running quite well over 2 years. And now we're also developing our technology for TOPCon, like for tunnel silicon oxide and polysilicon with PVD. And for PECVD, we are the only using the horizontal PECVD with ICP, CCP plasma source for crystalline silicon application. So actually, our ICP source and CCP source already being used quite a long time. We have a long time R&D results for PECVD, but before it's in these cluster tools, it's quite small. Now we give this long linear source, which with big area. So now we are using it for both PERC, PERT, or anything PERC plus, and especially for TOPCon, for tunnel oxide and polysilicon. And for this platform, Generous is this platform name. So we have we have the same for PECVD and PVD. We have the same chamber, same layout, same pump. So we share a lot of same construction part. The difference is the plasma. So for like here I listed for the beginning. Then you go through to the load log and then go through to the process chamber. Afterwards, you go to this lift in the end. Then the carrier will load down, and the whole carrier will come back from the bottom of the machine. Then come back to the unloading stage. So this is our layout for this platform. It's shared by PECVD and PVD. So and it flexible for different wafer size from M2 to M12, and it share very good layer uniformity, like within 5%. And the highlight is high throughput. For PVD, we provide 10,000 wafer per hour, and for PECVD, we provide 6,000 wafer per hour for M2 to M6, but also possible to upgrade to 10,000. So now let's go for the crystalline silicon solar cells. So here, actually, I think many people are already very familiar with this upgrade technology for crystalline silicon solar cells. And here, I just highlight this PERC to TOPCon and heterojunction. So if you only see the efficiency limit, maybe TOPCon has more space to improve. But we need to highlight this is more like simulation results. In reality, if you do also TOPCon structure in front, you have less optical absorption for the solar cells because it's polysilicon. So, but compared to heterojunction, TOPCon has one clear advantage is it can be upgraded from the PERC line. So you need almost 2 or 3 machines you can upgrade to TOPCon. But for heterojunction, you need a totally new machine, but it also has its advantage because it has only four process and very easy process flow and very good passivation performance of it. So both of these two technologies are competing or are ramping up very quickly in these 2 years. So let's go first for heterojunction. Here I highlight the main advantages for PERC to change to heterojunction. So simple process flow and low temperature process, especially for when you go for the module. The bifacial structure now is also coming to the market very much. So this for heterojunction, we have intrinsically, it's very good for bifacial structure. And in the module, it do not show any LID and PID, which is light-induced degradation and potential-induced degradation, which gives you more profit for the module part. And so, but actually, heterojunction already being a very long technologies, but it's only coming to the mass production or starting to the mass production in these years. The main reason I listed here is 3 parts. First is high cost, high standards, and reliable process for mass production. For the cost, it can be the first preliminary equipment investment, especially like PCVD, PVD. And later, when you really do the mass production, you need to counting for the target utilization, the temperature, the low temperature silver paste, and also like the chemicals usage during your production. So this is a directly course we can see, and the high standards. I think in the previous presentation, many people say heterojunction process is more or less a semiconductor process, which means it need more high standards for the cleaning, for wafers, for deposition of amorphous silicon with hydrogenated and also with TCO. Because it has very less process steps, each steps can make very big impact on the end solar cells performance. So this is also we need from machine point of view, we need to protect or like maintain all the high performance of the process in each step. And the last is a reliable process, which like the yield and the efficiency of your equipment, of your process. So here in the right part, I list our singular solution for heterojunction. Although we didn't mention the wet chemical part in this presentation, but I just shortenly listed here. So from cost point of view, we are encouraging the large throughput of all the machine, both chemical process and our PVD. And our PVD already running in very stable in the field over 2 years. So we have very good process baseline, and also we already get a lot of production data. For example, our target utilization can be over 80%, which is very good in the market, which can decrease the cost of ownership a lot. And we also developing a copper seed layer for copper plating for because this silver paste it's also a very big part for the cost of heterojunction, and also ozone-based chemical process which give you more renewable, environment-friendly process and high-efficient process for chemical process. And our running machine in the field, which already give a very average production efficiency over 24%. Here I list the 24.2. Actually, it's in the end of last year's efficiency. Now it's even more. So here is process flow. It's simple process flow for heat junction. So I think most of you are very familiar with it. So I will directly jump to the PVD process. So here I listed some requirements for TCO in the heterojunction solar cells. So the highlight here, first you need to maintain the ITO, the TCO performance, like high transmittance, low sheet resistance. But importantly for our PVD process is sputtering damage, because our ion bombardment from the sputtering jumper from sputtering mechanism is very strong to this several nanometer film for amorphous silicon. So how can you manage to reduce this sputtering damage during your design of a magnet bar or magnetic field is very important. And for TCO process, we need to maintain 200 degree for the ITO process or for the whole process. So how can you maintain the uniformity of this temperature? And so it's also very important. And in the end, from your design of the machine, you can maintain the uniformity of thickness as well as the temperature, and also need a less breakage machine compatible for different wafer format, since now there is no unit wafer format in the market. You need to compatible from M2, M6, even to M12. So in the end, is a large scale production machine with high throughput, provide for or offer this 1 gigawatt or over 1 gigawatt production. So just now, I already mentioned our layout, so I will not repeat it. So here is the features, like inline deposited both front and rear side of ITO coating, and the high utilization of rotatable targets, flexible for the different wafer format, and our high throughput machine. So here are some, I will share some production data for our machine in the field. So first is the the transmittance and sheet resistance. So here, as you can see, as we variate the oxygen ratio in the gas, we can get different performance of TCO. But for TCO, the trade-off between the optical and electrical performance, you need a process window, because, like for example, for front ITO, you probably need high transmittance. For sheet resistance, you can have more tolerance. But for rear side, you don't really care much about the transmittance. Then you will highlight for sheet resistance. So you need a process window for your machine. So as you can see in this green area, you can very easily to control your process to get the ITO what you want. So here the transmittance over 85, even over 87 is very easily to get. And at the same time, sheet resistance can be lower than 50. Actually, it's around 30. Around 30 is possible. And the second is the one I mentioned for the sputtering damage. During the R&D work of our PVD, we're doing a lot of research on the magnet bar design. So from left to right, you can see the balancing and also the magnetic field difference of our design. So from the production results, you can see after the optimizing our magnetic field, our passivation performance loss after the PVD can be lower than 3 millivolt. This is only the beginning of our optimization of process. Actually, after 2 years running and optimization of process, this decrease can be decreased more. Actually, now after your ITO deposition, we even can have higher IVOC in the production, but not that much. But like within 10 millivolt, it's very stable. It can be achievable. And the third is the heater. Here we see the right is it simulates the carrier which we had, like 8x8 carrier. These numbers means each wafers. We put 9 wafers on this carrier, and we put thermocouples to testing the temperature all the way during the production. So then from the data, you see our temperature can be well controlled within plus and minus 4 degrees. So which is a very good uniform machine for this process. And in order to get this good performance, we use this multi-designed heater. So you see in different panels, you can individually adjust the heaters. So you can adjust the heaters with a specific area. So you can get a very good heating performance in this machine. Actually, this heating is also used for PCB. So it's all these platforms, they share this good performance on the uniformity. And next is the thickness uniformity. As you know, the thickness are very important for ITO and also for the cell performance, like the visualization inspection. So as you see in the right side, you see these blue wafers, but you see some blue, deep blue and light blue. It's not coming from the thickness different. It's just coming from the shadow of the machine, since this carrier is under the machine. So we take a picture when we adjust it, you see it. So, but when you check the thickness uniformity, you see here is the deviation of thickness on the carrier. You will find the uniformity is very good. Like in the data, it's within 2%, but what we provide it's 5% between carrier and within single wafers. So it's a very good uniformity for our PVD machine. And the last is one also very important for inline machine. As you know, the carrier come and leave, you need a very high and stable venting and pumping process for this. As if you because this will affect your cycle time, as well as it will affect your wafer position during the pumping and venting process. So here in the left, you see our test for venting and pumping over 100 cycles, but each time the pressure in the chamber are very stable, which give you little movement for our wafer in the chamber. And which also, since it's lying down on the carrier is flat, so there is very little, very little breakage for our machine. And here is I listed some throughput numbers for our machine. In the right, you see generous 3,000, 6,000. This names is just the throughput for this different machine, and this 10,000. All of this is for wafers between M2 to M6. But for even larger wafers, we will have a little bit less throughput. So it also very dependent on the design or the plan for customers' factory. So here is a summary for our PVD used for heterojunction. As you know, this is already running in the field over 2 years, so it's quite stable and give very good performance for heterojunction. And now we are targeting the high throughput over 10,000 wafers, which is very good for gigawatt mass production lines. And for the cost of ownership, we have very good target utilization, over 83%. So which is very, very compatible or in the markets. And except for heterojunction, we also coming for TOPCon. Actually, when you join or when you talk with PV colleagues or PV people, then you will find in these years the competing between TOPCon and heterojunction are serious. But in these years, you find more and more companies are planting or starting the TOPCon factory, or all the PERC lines, they will leave some space for upgrade for TOPCon, which means TOPCon will be a very fast in the market, even than the heterojunction in these recent years. So here you will see this is the first or the highest advantage for TOPCon in the market, because it can share some common machine with PERC. And in generally that we only need a tannal oxide and doped amorphous polysilicon on the rear side. Then you can change not a P-type, but you can change a P-type or N-type PERC to TOPCon structure. So in this structure, we have 10,000 for chemical and also PCVD or PVD machine to fulfill this tannal oxide and this polysilicon. So here is similar for a bottleneck and also our solution for TOPCon. So the highlights is this tannal oxide compared to amorphous silicon in heterojunction. It's also very sensitive for your process. Whether you use a wet chemical or PCVD process or some other process for thermal oxide, it really depending on your process and also your machine. And this single side deposition for polysilicon is also a bottleneck, especially now in the market. Most people choose LPCVD to do this. Then it's very clear wraparound, which you need another extra wet chemical to remove it, which will make your yield a bit lower than normally PERC. So this all the bottleneck for to go to mass production. So this is also the reason or the ambition of our PECVD solution and the PVZD solution for this, because we want to use single-side deposition tools to make the tannal oxide and polysilicon, which give you just a single-side deposition without extra chemical cleaning process. And here is our main system description of PECVD. So here in the right, you will see our lab tool for PECVD. Although it's a lab tool, but it has same chamber size with our production. It's just a chamber. It's not that much, but one which can be used for different tests. And as you see, we have also compatible for different size of wafers. And we already tested many different dielectric layers for crystalline silicon solar cells. For example, for PERC, we tested aluminum oxide, silicon nitride, silicon oxide nitride. It's already proved and tested. But for TOPCon, we also did a lot of tests and get very good results on silicon oxide and polysilicon. I will share more data later. And our unique point is we use linear ICP and CCP source for depositing this silicon oxide and polysilicon, which will give you very high deposition rate. Depending on the different materials, this is a general rough number, like around 100 nanometer per minute. And also in our horizontal platform, which can give you a very large throughput for this machine. And we have very...
Mrs. Sheng, I'm sorry that I need to interrupt you. You have another maximum 1 minute left. I'm sorry for this. It's very interesting, but we have 2 more speakers. 1 minute.
Yeah, thank you. Yeah, 4 minutes, yeah.
No, 1 minute.
So I will... Yeah, so here is our solution for the roadmap for this TOPCon. We use ICP PECVD to depose tannal oxide and polysilicon. Here is intrinsic, which we can already offer now. And for CCP and PECVD and PVD, actually PVD we already also can both of them are under development. We do a lot of cooperation with them, with different institutes and companies. And here is the main results for TOPCon. Actually, we have very good passivation performance for our polysilicon deposited by PECVD, and also with our tunnel oxide PECVD and plus intrinsic polysilicon, we also have very good passivation performance. So actually, for the thing is for PECVD, for TOPCon, the thing is one best is the wraparound. So we will give you a no wraparound top polysilicon with PECVD deposition. So on the right side, you see very clear, very normal wraparound from LPCVD, and the PECVD, there is nothing you can see. Probably there is something on the edge, but actually you cannot see anything, and it's also difficult to check there is anything on the right. And also blistering, which can happen very often in the PECVD process, for example, for silicon nitride. So actually, we're also doing a lot to optimize it. So for our optimized process, you see, there is nothing. The pink side is blistering from other PECVD machine, but for left side, you see nothing for blistering. Actually, this is a highlight for our, it's almost to the end. So, but there is one thing I want to share is our solution for PVD. Deposit the polysilicon and the tunnel oxide. For we also did a lot of tests with ISFH and also some other company in China and in EU. So you see, we have very good passivation performance by PVD deposited tunnel oxide and polysilicon. So over 730, which is very promising, real single site deposition tools for TOPCon. So we're also looking forward to our R&D results for PVD solution. And here is the summary, a general summary for this generous PVD PECVD platform. So here the throughput, the efficiency, so it's our highlight for this. And in the end, I want to highlight, even today, we only mention the vacuum machine, but actually we also have Silex 2, Silex 3, which work very good for a heterojunction cleaning process, cleaning texturing process, which now is offering very high throughput for M2, M6, over 13,000 wafer per hour, and even for M12 with 7,200 wafer per hour. So for highlight for Silex, we use very good, very environment renewable process for ozone cleaning process. So and we also have many technologies, evaporation, sputtering, which can work for perovskite tandem solar cells. We're also doing a lot of cooperation now. So hopefully we can share some informations, updates next time. And in the end, we have these lab tools for all the chemical and PVD, PECVD tests. If anyone want to test their heterojunction or TOPCon performance process, welcome to cooperate with us. Thank you very much.
Thank you so much. So you brought it to a good end, and I think that was very good for everybody. And I would also like to thank the operators that they are flexible enough. They are our lifeline, and that is all possible.
Thank you very much.
Yes, a very good morning to all of you. My name is Dirk Kaisers. I'm the segment leader for the distributed energy management segment for the EMEA region, working with Eaton and really in a long time being in the photovoltaic industry for nearly 15 years now. And actually, I'm very happy to present now the first time at the PVSEC. It has taken a long time, but finally I'm here. And this morning I would like to present to you some different stuff that what we heard before. I'm talking about our solution for the solar power station when it comes to the medium voltage range. So, I mean, like as Eaton, we are a global company. We have roughly 100,000 employees and have a turnover globally of 17 billion US dollars, and are heavily involved in power electronics and in power systems. And we do this because we would like to help stopping the climate change with power management technologies and services that are fit for this purpose. So, and I mean, I think like all of you, we are aware that we are going through a really intensive transition, which is called the energy transition. We do see that the transport is going to be electrified. So there will be like an increase in global electricity demand alone by the transport sector of 27%. We see globally an demand increase of electricity until 2050 of 57%. By far, the most generation will come from the renewables, and here as well, like we see like a really heavy growth path. And I think like you have seen the recent communications, for example, by the European Commission, which are now increasing and accelerating the speed of this transition, and together, for example, as well with the green hydrogen initiatives that we do see, we see even a more sharper growth plan for renewables, and especially for solar and for utility scale solar plants. So I mean that's like kind of the background story, and that is why we are now heavily focusing on utility scale solar plants. So saying that that we are now concentrating on utility scale solar plants, obviously for a solar plant you need medium voltage switchgear. Unfortunately, not every switchgear is sustainable. So, and saying that, we as Eaton, we have been like the first company that actually has produced SF6-free switchgear. So SF6 is the most aggressive. It's the most aggressive greenhouse gas. So, and it's really harmful to the planet. It has been banned in almost all applications apart from medium voltage switchgear. And the European Commission is now reviewing the F-gas regulation, which is as well regulating SF6. They will review it in Q4 this year, and most probably a ban will occur. And we strongly urge you as well to get in contact with your local politicians to push them to help to get this really harmful gas out of our atmosphere. So, and we have these SF6-free switchgear in our portfolio for a long time, and as well now we are able to combine this with our eco-sensitive transformers, which we produce in our production facility in Ankara, and so we are being able to get this into a containerized solution, and to bring you like a really ready-made solution for your medium voltage grid within the PV park. So we are offering you a pre-assembled plug-and-play substation. So this is specialized on photovoltaic plants. It includes the SF6-free switchgear. It includes the transformer, and it includes as well the low voltage assemblies in one enclosure. So normally we build this in a standard container, so it's shippable, and it would arrive on your site, and then you just really need to plug it in, and it will go. So it's plug and play. It's safe because we tested in our facility. You're actually always on. This is as well like a very nice feature, and we are using actually. Not fuses, but we are using breakers. So that means that you can switch on and off, and you have like a higher uptime. And obviously, as Eaton, we can provide you with like really high quality, and this as well reduces the risk of a downside. So here you see like some products that we put in there. So you see the Syria, which is the SS63 switchgear that we're producing in Hengelo in the Netherlands. You see here the liquid immersed transformers and the X Energy main unit for the low voltage part. All of these we are able to bring in different components and then different megawatt sizes to be able to comfort all your needs when it comes to the solar park implementation. And as said, we offer as well from the enclosure. We are offering two different options at the moment. We have the option of bringing it in completely containerized in a standardized container, as well as a skidded model version, which is like semi-containerized and which would be like more fit for purpose for southern countries. Optional, we offer as well like the platform, so to have like an easier access, like with the stand and the access stairs. We offer air conditioning, the low voltage distribution on the 230, 400 volt level, as well like distribution for lighting and outlet sockets, and as well the fire detection systems, which in some cases is definitely mandatory. So, I mean, like this was like a really short presentation. So I just wanted to, to let you know that we have like these kind of solutions, that we are ready to work with you, and we would like really help you to build a PV plant that is SSX free and to help the environment in an even more effective way. So, and please get in contact with me. So my email is dirkkaisers@eaton.com if you're interested in working with us. So that was my presentation.
Thank you so much. He is from Atotech in Germany, and he will present us the Atotech approach to texturing M12 wafers up to 1 gigawatt on one wet bench. And so this is the title. There's also Q612, which sounds very secretly, but Dr. Knoch will certainly enlighten us what it means. So we're looking forward to your presentation. And if you can keep the time below 15 minutes, then we would have give time to Dr.
Okay.
to finish your presentation.
I'll try.
Okay, so thank you very much. It's your floor.
So I'm Jerry Knoch, the Managing Director of Atotech. This morning I want to guide you to our flagship product, the Q612, which is the wet bench for texturing M12 wafers up to 1 gigawatt capacity. It's our latest product, and our focus for the PV sector is general design and manufacturing of wet benches. So for texturing mainly, but obviously also for other etching and cleaning processes in the solar cell manufacturing. You have no idea about Atotech? That could be. And I want to take you a little bit through the history of Atotech. The core team, which are people who've worked together for many, many years, more than 20 years, some of them have been active in designing batch wet benches and manufacturing them for, for a long time. And they have worked ever since on these products. So we have a lot of experience for the PV sector in batch wet benches. But if you haven't heard of Atotech before, this may be because we've only been founded in 2015. At the time, there were some troubled periods for some colleagues of the company, and then my then colleague Matthias Niese and myself decided to establish Atotech as our own company and take our own destiny into our own hands. And today, 6 years later, we are a small company, a solid company, 12 people, but we are just not as well known as our main competitors like Rena or Singulus. And by the way, Matthias Niese, whom I have just mentioned, he's our technical director. So now you have a rough idea about Exotech. So, but why should you come to Exotech and talk about your wet processing needs, your cell manufacturing? Well, I think it's the innovative part that is important, and I want to run through this for you, how we've developed wet benches in these 6 years. We call them the Q production systems. And now there's some enlightenment on what this Q612 or 612 is all about. Q is the name of the tool, and the 600 means the number of batches or number of wafers per batch. So a Q600 would be 600 wafers per batch per tank per processing unit. And this is now translating this into a capacity. This is roughly 800 megawatts of one tool. And we have obviously various sizes, so the Q400, 200, and so on. And the smallest unit is our manual or automatic lab unit with the Q25. So there are just 25 wafers in one tank. Let's move now to what you may need to the future. And look at where we've come to so far. As I said, we started in 2015, and at that time it was the Q200, 200 wafers per batch, just doing 3,000 plus wafers. The Q400 wafer size systems were already on the market, and they became available from Exotech in 2016. This wasn't good enough, obviously, for one of our customers, because he pushed us strongly into the Q600. This is 600 wafers per processing tank, and you can push out about 10,000 wafers an hour out of this unit. This was in 2016 already. So we put it in production. Everything ran smoothly. No trouble. We launched it on the market in general. Unfortunately, there wasn't that much interest at the time, so it lingered around for almost 5 years, and it's only become of high interest nowadays. So you also see here that the Q25, the lab tool, was introduced in 2015. At the moment, we have more than 25 production tools in operation 24/7. And just a brief introduction to our tool. This is the latest innovation. It's a particle-free loading system with carrier-specific weighing. And you see the carriers transported through the wet bench. This is a Q410, and I'll get back to this in a minute. So after processing, the carriers leave the tool again. Okay. So the big question is now, where will the future take us? There are a few questions or a few highlights. This is technology. It's the throughput and the wafer size. This is already the sheet for the wafer size. On the technology, I don't want to engage into the discussion what will be the market leader or the dominating technology in the next few years. Anyway, IBC is the top in performance, but it's price-wise very costly. So I think it remains a product for the niche market. Recently, the focus of our deliveries has been heterojunction. So most of our recent customers have added our texturing tool to their heterojunction line. So we are also familiar with these specific requirements. On the throughput, we've just done most of that. I just want to stress again that already 5 years ago, the Q600 could do 10,000 wafers per hour. And now we come to the wafer sizes. This to me is a, a strange situation. It's a race at the moment where I don't know it's going to. We have half cuts, third cuts, M10, M12, everything's on the market. Anyway, it's the M12 which is really big, and there's the issue of the thickness, and large wafers and thin wafers are very difficult for batch wet benches. So it's a steep hill to climb to get this running well. Thin mono wafers can be as flexible as a sheet of paper. So if you talk about 120 micron wafers, it's really difficult to process. Anyway, we are continuously working on these challenges of such large and thin wafers, and in which case you need to consider both the wet bench itself plus the carriers, which take the wafers and through the wet bench. So this has been a good reason for Exotech also to offer carriers designed and manufactured in-house. So now we are here looking at the different names. You see the Q200 and 400, 600 again. We had to change this now with the coming up of M6, as we had to create a new M10 and M12. We had to create a new platform, which was bigger. So now you see a Q406. This would be 400 wafers up to M6 size. And you see also this flagship number of Q612. These are 600 wafers of M12 format, pushing out maybe 10,000 wafers, could be even more, and subject to the performance of the wafer. This relates to 800 plus megawatts. So this is why the title is on the up to 1 gigawatt. We are approaching this. I haven't seen any M12 heterojunction wafers also with a very high efficiency, but this may come. We don't know. We currently have in the field a Q410. So this is 400 wafers for M10 size, very special design. And we are working on our Q612. We are very confident to get this right straight away, as we have 5 years of experience with the Q600. We have experience now with the M10 size, which is basically an M12 type tool with some features so that you can just run M10 to save some chemicals. Okay, so you've seen how quickly we have developed all our tools. And there are the carriers, of course, I've just mentioned them, produced in-house as well. There is chemical supply and disposal systems available to complement the tools, be it for the lab or be it for mass production. And okay, now this should have been all good reasons for you to talk to Exotech when you're looking at wet processing equipment. Once again, 20 years of experience designing these tools and manufacturing them. We have always supplied to top-class manufacturers, even in the past, and today we are still there. Because we are small, we are very flexible, and our focus is on the customer specific or maybe even unique need. The Q600 was such a thing. The Q410 is a similar design, a similar unique creation. And when you talk to Exotech, there are two guys you talk to. This is myself, but it could also be Matthias when we are executing a joint project. So the two top guys are your contacts. So what better attention could you expect? Now, before I close, a brief glance at our manufacturing area. This is not the latest picture, but it shows you how we build our tools in-house, 1,200 square meters, and based on current tool design, we have a capacity of about 6 gigawatts on Q400 design, or 8 gigawatts on 600, the Q600. Q612 would be part of this. So I hope you've got a good feel for wet processing equipment from Exotech. I would be looking forward to talking to you for further discussions of your requirements. Thank you very much.
Thank you so much, Dr. Knoch. And at this point, I also want to tell again the audience, you have a possibility to chat first with Mr. Knoch and then make also a video appointment. So make use of this and get in touch with the presenters. Thank all presenters. They were very good, very much in time, very interesting, well-prepared presentations. We had a good audience, so it's more than a classroom full, partially 35 people watching you. And so this, I think, is shows how we can, even when we cannot meet personally, get some good contacts. And I hope that the audience makes use also for making appointments with you. With this, I want to say goodbye to everybody, wherever you are, and hope I see you soon in another occasion and maybe in reality. Goodbye and have a nice afternoon and enjoy the whole EU PVSEC. Thank you.
Thank you very much. Thank you.